When we talk about soil behavior or soil properties, one very important aspect is to understand the soil stress strain behavior. So, which is we talk about it already when in the static under the static loading from the previous class. So, for example, remember when we do our foundation design. For example, you have some sort of loading, could be from structural load passed through the foundations, and you're adding the bearing pressure to the soils. So you can imagine you create kind of like a slip surface when we try to mobilize the ground. So we want to know how the stress is cutting through the loading passing through and soil elements. So the loading here is kind of like providing on this piece of soil elements, you're providing kind of like a shear force, and this shear force adding on our soil elements, right? We have a loading trying to deform the pieces of the soil. And I'm extracting the deformations. The movement's supposed to be small or being progressive, but if we look at a time slot a failure, so the amount of deformations here is kind of like the string part. So this is displacements, and the stress is the loading. So loading is come from any construction activities, like this time maybe from the foundations, and passing as to the soils, so you kind of like a shear stress. And for this particular piece of soil elements, we know the original heights. So the height of these the soil elements here, and we define the strength, the shear strain here is the amount of deformations divided by the height of the soil elements. So the shear strain, which is the letter gamma here, the Greek letter, is the amount of deformations divided by the height of the soil elements, and then times 100%. So that will be your shear strain. And we have the loading. Again, the loading is tau. The shear load when we get on the soil elements, so there's a shear stress. So the shear stress is inducing the deformations. The deformations can convert to the shear strain, and this is deformations dependence behavior. So that's why we call this as a stress strain relationship or stress strain behavior. Is the shear stress will be a functions of the deformations or the shear strain. So that's why we get the stress strain curve. So remember, if you have taken the lab class, you have seen the direct shear test when we load on the sand samples, and you record the loading, right? So you kind of cranking the shear device. You give your shear displacements or shear deformations or shear strength, and the load cell will pick up the shear load and divide by the area. You will find out the shear stress. And in 366, sorry, not 366, the 566, when we talk about soil mechanics, we also talk about the stress path in the PQ terms, and it tells you how the stress path look like, right? If this is a loose soil, so we talk about all this in 566, and then this is we talk about the critical state soil mechanics, and this is the critical state line. So this is the critical state line with soil friction angle there. So that will be the soil mechanics part that we talked about before. when the soil is subject to a static loading. So what happened in earthquake? Earthquake is not providing like a static loading, but you provide a dynamic loading. So when earthquake happens, it kind of like a upward propagating a shear wave. Let me just screen maybe. So you will be when earthquake happens again. It's just like the earthquake ground motions record they play with in lecture 2. So those upward propagating shear wave will travel through your soil elements. So instead of just like a static deformations that the soil elements will the soil will experience, in fact you will go kind of like a back and forth. So so you kind of like a sine wave going through the soil elements, and you will go back and forth. You will go like deformations can go one way, and then like in other when you like reverse the loading, you can go the other ways too. So it's kind of like going back and forth, and you will creating like the displacements here back and forth, right? So this is still the deformations, but you will have at two different directions. And we still have the same for example, we still have the same soil specimen height, and this is kind of like again the upward. So this is still the upward propagating shear wave. That is adding on the generate from the earthquake. So in terms of the stress string plot, again, like everything ties back to the stress string behavior. And now since this go back and forth, so it's not like going one directions only. You can go both positive and negative. And again, this is the same thing. This is the shear strain induced from the shear displacements. Could be like from the positive side and also from the negative side. And this is the shear stress. So you imagine like actually the loading adding on it will be so this is the soil, right? This is kind of your axis, and you can kind of like go back and forth like a sine wave going through it. So you could have your positive loading, and you can also have your negative side of loading. So the stress string plot will look like this. First, you will go positive on the stress, so this is the positive part, and then you generate positive deformations. And then like you go up, go down, and then go to the negative, and then you would generate like a negative displacements too. So this is kind of like the hysteresis loops for the stress string part under cyclic loading. And this is at kind of like assume this is your first loading cycle, and then there with a bunch of different loading cycles going through your soil elements that you're looking at. And then like as the more loading go by, the soil start to fail, and then we generate more and more displacement. So you imagine this cycle with this keep going back and forth, and the loops or the hysteresis loops there will become larger and larger, and at some points at failure you will have a high displacements. So you could have a loops something like this. You're generating a huge like amount of displacements. So that would be the shear strength at a higher shear loading. So this is kind of like the stress path for static loading here, and for cyclic loading, again the same PQ port, and now this will go back and forth. So this could be your first cycles, and then you will be keep loading it, and then like realize this is the mean effective stress, right? The P is equals to 1/3 of sigma V pi plus 2 times the horizontal stress, and as this can go very deep in solid mechanics, but this is earthquake engineering class, so I don't want to go too deep into solid mechanics. But if you want to understand more about this stress path, like you feel free to come about. Feel free to stop by my office hour. So the stress path here under dynamic loading could be a little bit more complicated than the one that you learn in 566. Everything is based on static loadings, and definitely this topic here we talk about here is getting to the PhD level. And this, we can spend like a couple weeks just talk about dynamic soil behavior, and this kind of like our scope of the geotech earthquake class. So here I don't expect you to know too much about it, about the stress path under the dynamic loading. But what I do need you to get out from this is the big picture, or like the transitions from like the static loading to the dynamic loading. What kind of loading on the soils elements, and what did you expect to see? And the stress path, if to complete this, like you will keep loading until you fail, you lost all the vertical effective stress, and then you will start to see the butterfly loops. So we see a lot of this like in the laboratory Taylor of the cyclic loading. And this slope here, actually this is the critical state line. So this here, the slope here is give you the friction angle, and this critical state line here pretty much is supposed to be the same as the slopes, the same as the one that you obtained from a static loading, the same stress path. So this is kind of like a quick picture on about the dynamic loading, or the dynamic stress ring response.